Okay,
Excellent.
so our next speaker is Axel Hahlin, who's going to be telling us about the magnetic field of the eclipsing binary UV Psc. Please take it away.
Yes, thank you very much. So as mentioned, my name is Axel Hahlin. I work at the Department of Physics and Astronomy at Uppsala University as a PhD student, and I will be talking about the contents of an upcoming paper about the magnetic fields of UV Prism. And first, I was just thinking to introduce the star itself. So it is an eclipsing binary. The primary component is very close to the, or similar to the sun. It's a G-type star, and it has a smaller secondary component of K3. The system has a high inclination, as of course implied by its eclipsing nature, and previous studies have found that it is magnetically active. In particular interest for UV Prism, this magnetic field has been used to sort of solve some of the peculiarities relating to its properties, particularly that it has been found that it has a slightly inflated radius, or both components, and that there has also been a large age discrepancy discovered, specifically by Popper in 1997, where Fudge found that this secondary star was estimated to be about twice as old as the primary. And this can be seen here in this plot made by Faden and Chabouir, who made attempts to mitigate this discrepancy by using magnetic fields. Specifically, the observed radius for UV Prism A and B can be seen as these colored horizontal bars, and the stellar evolutionary models without magnetic fields are shown as these solid lines. And we can see here that they cross this observed radius at different ages. But by applying or introducing magnetic fields to these models, he was able to make them cross this area simultaneously or at the same age, which shows the power of using magnetic fields in these situations, and also why magnetic fields sometimes needs to be accounted for when studying these types of things. And this is the primary motivation as to why, or one of the primary motivations as to why we're interested in magnetic fields around this star. And we studied the magnetic field using the Zeeman effect, of course. Many of you are probably familiar with it. Once again, short recap. We have polarization signals, and this allows us to determine the direction of the magnetic fields as a vector quantity by observing different forms of polarization depending on from where you are looking at it. So if you're looking straight or in the direction of the magnetic field, you will see circular polarization. And if you're looking sort of on the plane or horizontally or perpendicular to the magnetic field, you see linear polarizations in the different components. And another effect that is commonly used is the broadening of the line itself. So what happens is you have the pi components in the center, and then you have the blue and red shifted sigma components that are, well, shifted a little bit. And this usually results in line distortions that can be used to infer the overall magnetic field strength on stars. Another effect that is, I guess, slightly less commonly used is that this broadening also causes an increase in equivalent width due to the fact that when these sigma components separate, the saturation of the line goes away, which allows the overall line to absorb more photons. And this is also useful because this equivalent width increase is not sensitive to, for example, rotational smearing, because the broadening in effect is, you can only use that on stars which has fairly low rotation rate, but this equivalent width can be used on basically any rotation rate, which is good because UV Prism is a quite close binary, as we will see, and it has a very high rotation rate of about 70 kilometers per second. Our observations has been taken on using the Espadons spectropolarimeter at the Canada-France-Hawaii telescope. Particularly, the observations were done by the Bynamics project, which specializes in studying various binary stars. And we have obtained both intensity and circular polarizations. So Stokes I and V. In total, 18 observations were obtained during a period between August and September of 2016. And in order, as has been pointed out before, we need to use a multi-line technique in order to properly see the magnetic signal in the circular polarization profile due to the relative weakness. And the result of these for some phases can be seen here. So here is the intensity. We can see the primary line, the line corresponding to, or the average line corresponding to the primary, and the average line corresponding to the secondary. During some of the observations highlighted here, we had some stellar contamination, or specifically the sun contaminating by reflecting moonlight, which had to be removed for some of the observations. And on the right here, we have our circular polarization. We can clearly see magnetic signals here for the primary, and also here for the secondary, which indeed indicates that there are magnetic fields present on the star. We also performed some orbital solution and disentangled spectra on the binary. Specifically here on the left, we can see the orbital solution that we have obtained. The red circles are our own observations, while the blue diamonds correspond to observations from Popper et al. So we can see here that it has fairly high orbital solution, and this allows us also to obtain fairly accurate masses of the system. The disentangled spectra is used for the intensification study. Once again, we want to study the individual components without blending, so we disentangle them. And this is basically done by taking all our observations of intensity spectra and using the radial velocity information obtained and essentially extracting the spectra for each star individually. And this can be seen here. We have the spectra for the primary and for the secondary. And we can also compare it with the observations, looking at this black corresponds to the observation, and the red corresponds to the combination of these two spectra with radial velocity shifts. And we can see that there is an overall good agreement. There is an exception out here, and this simply comes from the fact that we have cut the spectral disentanglement area here, and this results in some artifacts on the sides. But we did not analyze this part, and it shouldn't affect our results. So, Sim and Doppler imaging has been talked about before in previous talks, so I will not go into detail. I will instead just talk about some of the differences between doing Sim and Doppler imaging on a binary system compared to a single star. And what you have to account for here is that we have to model the system in its entirety, not just as separate stars. And this means not only the star itself, but also the sort of orbital motion of the star and how they eclipse each other at any given point. And this can be seen here to the right. We can, for example, see an eclipse or a slight eclipse here on the top. We can see the maximum separation of the system here. So we can see that they are indeed a very closely tied system. And we can see another binary here with another eclipse where the secondary component is hidden behind the primary. Now, the stars are very close, as we can see, and they are tidally locked. And this justifies our use of the Roche-Loeb geometry, which means that we model these stars as co-rotating, but they are also distorted by the gravitational effects of each other. It's not super strong, but we can see a slight tendency that this side might be slightly more elongated than this side. Also for reference, these points correspond to the surface elements of the star used in our CDI recovery. So each of these are one of the points used during the recovery of the magnetic field map, which we can see here. So we have obtained magnetic field maps for the primary and secondary components together with the brightness. Here on the right, we can see all the observed circular polarization profiles. And we can see that they are quite significantly stronger for the primary star, which comes from the fact that we have the primary is quite a bit brighter compared to the secondary. And this sort of hides a lot of the contribution from the secondary in the spectrum itself. And overall, the strength of the field seems to be slightly stronger on the primary, with weak meridional components for both stars, which is a common occurrence in CDI inversions when you do not have access to linear polarization. One thing that you might see is that there is a lot of symmetrical structures. And this is something that I will go into in a little bit because we looked into this a bit closer. And it does come from the fact that we have a high inclination targets, which makes it difficult to distinguish the two hemispheres. And this is why we can see these very symmetrical structures in all components. But I will go into more details about the magnetic field symmetry in just a bit. We also have a look a little bit about the general morphology of the system, specifically how the energy is distributed over the different angular modes. So we can see here that the secondary component is very strongly dominated by a simple field. And this likely comes from the fact that its contribution, as you saw in the observations, is very weak, barely detectable, which means that simple fields is more likely to reproduce because we, of course, penalize strong and complex fields due to noise reduction. So this is a likely cause for this strong dominance of a simple field. But for the primary, we can see a lot more complexity. Dominate most of the energy, or most contributing mode is coming from the third order angular modes. We also have some general some numbers that might be interesting. For example, how colloidal the structure is. The primary has a quite colloidal structure, about dominated by colloidal, while the secondary is more evenly divided between colloidal and toroidal components. The axisymmetry is very weak on the primary, while on the secondary it is about an even split between axisymmetric and non-axisymmetric features. Once again, we have two different definitions, one only taking in the m equals to 0 modes, and one taking in m equals to half of L, depending on which one you prefer. So let's talk about the symmetrical magnetic field. We did an investigation by applying a known magnetic field to exactly the same geometry, and then seeing what CDI does. And to the left here, we have our known field, which is just a dipole that is slightly aligned off the rotational axis. And the reproduced results look like this, which is quite significantly different from our results. Not only is the field a fair bit weaker, but it is also not really sharing the same structure. It is a dipole, but it is entirely symmetric with respect to the equator. And this shows that there is a significant information loss when we're looking at high inclination targets. And we basically don't see any features that are antisymmetric at all. That is with respect to the equator. And this is a little bit of a problem, especially when we're looking at these high inclination targets, such as eclipsing binaries. And in the coming years, when we're looking at, for example, transiting exoplanetary hosts, which will also have a high inclination. And to study these magnetic fields accurately, this sort of issue poses a bit of a problem. So we did also look at a bit of a qualitative way to possibly solve this, specifically looking at linear polarization. And as it turns out, linear polarization isn't particularly sensitive to whether the mode that you're looking at is antisymmetric or symmetric. And this means that if we could reliably or more reliably detect linear polarization, there is a possibility to sort of break this degeneracy that I showed earlier, by basically being able to see the antisymmetric modes as well. So this is something that's very interesting in the future with upcoming next generation spectropolarimeters, such as Spiro and Quirus Plus, that this sort of the linear polarization detections might be utilized to more accurately map these features that are not visible otherwise. We also, besides looking at the general topology of the magnetic field, we also used Zeeman intensification to look at the more average small-scale field that is not seen by CDI. And to do this, we needed to find lines that are appropriately not blended. We have a high rotation rate, which can cause a lot of blending with nearby lines. And we also want a good sensitivity to the magnetic fields. And we use this iron multiplet that has been used in previous studies, specifically because it has a very sensitive iron line that also happens to not be blended in our case. And this is this blue thick line that we can see here, and showing in this plot, showing the equivalent width, the change in equivalent width as a function of magnetic field. So we can see here that this has a very strong sensitivity compared to other lines. And another unblended line we found was this red thick line down here, and it has a weaker sensitivity. And this is precisely what we want, or this is good because we want to be able to distinguish or disentangle the magnetic increase of equivalent width with other parameters, such as abundance, for example. And for the secondary, we can also see here that it's looking fine. We have a stronger sensitivity and a weaker sensitivity, but overall the sensitivity of the magnetic lines, or these lines, are weaker for the primary, which indicates that it's might be less, is not quite as suitable, and will result in higher uncertainties, but we still have something to work with. And the way we do this is that we perform Markov chain Monte Carlo sampling using the magnetic filling factors as parameters. And these are essentially parameters that say how large part of the stellar surface is covered by magnetic fields of a certain strength. Specifically, we demand that the sum of all these filling factors should be equal to 1. We don't want 200% of the star to be covered by magnetic fields. That doesn't really make sense. And we also have, and this also gives us an easy way to calculate the mean magnetic field that we obtained from the model by simply summing the filling factor multiplied by its corresponding field strength. as mentioned before, we want to disentangle the effect of the magnetic fields with other parameters. So we also include iron abundance in this inference. And we also include luminosity ratio. And this is because UV Psc has been observed before, and the luminosity ratio in the V band has been found to vary quite a bit, maybe between 5 and 6. No, 5 and 7. So this indicates that we should vary this luminosity ratio to obtain a good measure of that as well. We also include a rotation rate, V sin I, as a parameter as well. So we perform the Markov chain Monte Carlo sampling, and we obtain this spectral fit. So we have the two lines that we are working with. The black is the observations, and the red corresponds to our best fit. The blue line is the best fit parameters, assuming a zero magnetic field. So what we can see here is that for this iron line in particular, it's a very big difference. And modeling these lines without taking account into magnetic field can also result in some, well, problematic assumptions or conclusions if you're not accounting for magnetic field properly in these cases. The average magnetic field can be seen here, the posterior distribution of the magnetic field. It lands at about 2.5 kilogauss. So a quite strong average field strength all in all. And we also have these posterior distributions of other parameters. We can see that the filling factors in particular are very strongly dependent on each other. And this comes from the fact that intensification, as I mentioned earlier, is not sensitive to the line broadening. So we're not sensitive to the line shape as much as we are sensitive to the increase in equivalent width. And what this means is that a lot of one field components, for example, let's say we have a lot of weak fields on the star, that is almost equivalent to having a little bit of strong fields on the star. So, and this is why there is a very, very strong dependence here. Now, we also did the same thing, or almost the same thing for the secondary. The primary difference here is that for the primary, we constrain the abundance, and for the secondary, which is quite significantly weaker, we constrain the luminosity ratio. And the motivation for this is that the primary would be a lot more sensitive to the fluctuations in luminosity ratio than the primary were. And here's the result we can see.
3 minutes, Axel.
Yes, thank you. Here's the results. Once again, we have the spectral line. We can see the sensitivity is weaker here, as we expected from the plots earlier. And we can also obtain a magnetic field strength of about 2 kilogauss. Slightly weaker, but not significantly so. It's also an indication here is that this star seems to be slightly more dominated by 4 kilogauss field factors, and there might even be not a significant contribution at all from the 2 kilogauss filling factor. So how does this look compared to other stars? Specifically, we're comparing these two components to a sample of cool partially convective stars that have also been studied with the same method, specifically CDI and intensification of the same iron multiplet. And we can see that it falls on the kind of active side. Once again, it has a very high rotation rate, which usually corresponds to high activity. So this isn't necessarily unexpected. And given the fairly large scatter, the results are, I guess, largely compatible, or what we would expect from this star. The slightly underestimation might come, as I mentioned, from the fact that CDI is on the y-axis. The result from CDI might come from the fact that the magnetic fields of CDI gets underestimated due to our high inclination. But overall, it looks pretty in agreement. So just to finish off some things, here we have our obtained values from CDI and from Simon intensification. And this shows that, once again, intensification, the field obtained from intensification is significantly stronger. And it highlights that a lot of the magnetic field strength is dominated on the smaller scales rather than these large scales observable with Simon Doppler imaging, which is also something that can be seen in a lot of other studies. We can use Simon intensification once again on high V sin I's. I think from what I've seen, the UV Psc is the largest V sin I value that this has been successfully done on cool stars, which is good news. The only challenge is to find unblended lines. And high inclination poses an issue, but we've at least sort of tentatively said that linear polarization seems to be able to remove this degeneracy and allow us to observe antisymmetric magnetic field structures. And yes, that's it for me.
Thank you for that great talk, Axel. So I see Rob is straight in there with his hand up already. So if you want to ask your question.
Hey, Axel, thanks for nice talk. I was just wondering about this issue of the symmetry between the northern and southern hemispheres. Would you say that's only due to the inclination, or does the fact that you have to model two stars at the same time, does that come into it at all?
I don't think two stars are relevant. Once again, they have a fairly high rotation rate, so the separation is quite large most of the time, and I don't think that the double star would pose a significant issue here. You could argue that one thing that's an issue is, of course, that the signal of the secondary, which is quite a bit weaker, gets sort of hidden by the strength of the primary, which could be an issue for the primary. And even in our reconstruction, we can see that the primary is actually slightly more, is the weakness of the primary gets slightly larger, like, or how should I say, the weakness or the reconstruction of the secondary is slightly weaker than the primary, even though they started with the same field strength.
Yeah.
So it might be a bit of an issue for the secondary, but not for the primary, I think.
Yeah, I was just thinking kind of about when they're kind of partially eclipsing one another, is there some kind of cancellation maybe between the signals? But
I don't like it. There could potentially be, but then again, I think it's not. I don't think it's significant. And another fact that you can actually see is that when they eclipse, the symmetry is temporarily broken. So when you look at the circular polarization spectra of these antisymmetric features, during an eclipse, you actually get stronger signal because the symmetry is temporarily broken. So the eclipses could, in that context, almost help rather than break.
Okay, cool. Thanks, man.
And another question from Thomas Hackman.
Thank you for a very nice talk. I was wondering about this Stokes U and Q observations. I mean, obviously, the signal to noise will be very much weaker, and so is it? You can also assume that this star is rotating pretty fast. I don't know how far. I mean, the period is quite short, so. Is it really possible that you can get with Cry-Res, for instance, good Stokes Q and U observations of this target?
I am not sure about the specifics there, but yes, the rotation rate is about 0.86 days, and we're already accounting for we're already having to account for the like rotational shift. So we do kind of rotational smearing is already a bit of an issue that we have to account for. And this could, of course, be emphasized or increased by having to do increased. So I don't know exactly if it's possible, but this is, of course, also relevant for other high inclination targets, maybe not for this particular star, but it's an important something to keep in mind anyways. So for lower inclination, high inclination target with lower rotation rate, it could still be usable.
Thank you.
One last question from Emre Asik.
I have a very short question. Can you please show us the orbital phases in the maps of brightness and magnetic field? I mean, where is the kind of substellar point? Or
yes, I believe the substellar point is in the center.
Okay, so there's a kind of preference in those longitudes, it looks like, but of course we only have one epoch. Yeah.
Yes, so right now we only have